This is our team members.
Let me introduce about molecular orbital theory. A molecular orbital theory provides comprehensive framework for understanding chemical bonding by describing how atomic atom orbitals combine, enable prediction about molecule structure and behavior beyond simple Lewis representation. Now, let's talk about the objective of this topic. There are three objectives of this topic. First, construct and field energy level diagram for the atomic molecules. Second, predict molecular stability through bond order and magnetic behavior. And lastly, differentiate between localized bonding (VBT) and delocalized bonding (MOT).
Rules from molecular orbital diagram. First, when atomic orbitals from atoms combine, they form molecular orbitals. Each atomic orbital used will produce one molecular orbital. For example, two atomic orbitals combine to form two molecular orbitals, which is one body molecular orbital and one antibody molecular orbital. Second, electrons will fill the lowest energy molecular orbitals first, before moving to higher energy orbitals. If two orbitals have the same energy, electrons occupy them singly first before filling. This is Hund's rule. And third, one molecular orbital can accommodate only two electrons, and this electron must have opposite spin, which is from Pauli exclusion principle. And the last one is the total electron present in the molecular orbital diagram is the sum of all electrons contributed by the bonding atoms. For our discussion on molecular orbital theory, we have chosen O2 as an example. Let's begin by looking at how the molecular orbitals of O2 are constructed and how we can determine its bond order. Since O2 consists of atoms of the same element, it is a homuncular diametric molecule. To understand the electronic structure of O2, we must look at how the atomic orbitals of two oxygen atoms overlap. Oxygen has an atomic number of 8, with the valence configuration which is 1s2, 2s2, 2p4. When two oxygen atoms bond, just 16 total electrons are redistributed into molecular orbitals based on their energy levels. The focus is, however, is on the valence 2p orbitals. In the case of oxygen, the sigma 2p orbital is lower in the energy than the 2 by 2p orbitals. This is a specific characteristic of heavier homuncular diametric molecules like oxygen. So, to construct the diagram, we fill this orbital according to the off-ball principle, occupying the bonding level first, followed by the antibody levels. This distribution is what determines the chemical properties of the molecule. This is the diagram of molecular orbital of O2 that constructed before filling the electron. In the picture, we have an arrow as energy from low to high. On the left side is atomic orbital of oxygen first, in the middle is molecular orbital of O2, and the right side is atomic orbital of oxygen second. So let's start by filling the electron. Sin 1s and 2s of both oxygen is same total electron, which is 4. We fill in the electron for 1s and 2s the same. So for 1s and 2s, 1, 2, 3, 4. So the total is 4. Next, we fill in at sigma 1s as well as sigma 2s. 1, 2. And another 2, we fill in at sigma star 1s as well as sigma star 2s. 3, 4. So complete for 4 electron. Next, we fill electron into P for both atom of O section. So, the total electron into P for both atom is 8. So, we write like this. 1, 2, 3, 4, 5, 6, 7, 8. So, the total is 8. Next, we fill in the bonding and antibody electron. So, first for body electron, which is sigma 2ps, pi 2py, and pi 2pz. 1, 2, 3, 4, 5, 6. So, another 2 is we fill in the antibody electron, which is pi star 2py, pi star 2pz. 1, 2. We will write the electronic configuration. Electronic configuration is for the total electron in antibody and bonding electron. So first, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2ps2, sigma pi 2py2, pi 2pz2, pi star 2py1, and lastly pi star 2pz1. And for your information, star is shown for the antibonding electron. And also, as you can see, sigma 1s2, 2 is shown for the total electron that has in 1s order. Bond order show the strength of a bond of the atoms. It is based on the difference number between bonding and antibonding electrons. A higher bond order means a stronger and more stable bond. So for the uses of bond order are to evaluate the stability of a compound, to indicate bond strength, and to show whether a molecule can exist. That's all of these are the total what you can get when you calculate the bond order and what they represent for. A bond order of 1 represents a single bond, and a bond order of 2 represents a double bond, and a bond order of 3 represents a triple bond. A bond order of 0 or negative means no bond is formed. Fractional bond orders such as 1 over 2, 3 over 2, or 5 over 2 are also possible in some molecules. Let's calculate the bond order. So for the formula of bond order is number of body electron subtract number of antibody electron divided by 2. So for the number of body electron, we have sigma 1 s2, sigma 2 s2, sigma 2 px2, pi 2 py2, and pi 2 pz2. So the total is 10. So the next one is number of antibody electron. We have sigma star 1 s2, sigma star 2 s2, pi star 2 py1, and pi star 2 pz1. So the total is 6. So 10 subtract with 6 and then divided by 2, we get 2. So for the comparison, as you want to know, we have O2 and O2 minus. So for O2, we have the bond order is 2. It is larger bond order and a greater bond stretch and have shorter bond length. So the comparison for O2 minus is the bond order is 1.5. It is small bond order, lower bond strength, and the longer bond length.
Magnetism. There's two types of magnetism, which is diamagnetic and paramagnetic. Diamagnetic is a substance that not contain unpaired electron, and it repel a magnet, which different from a paramagnetic that contain at least one unpaired electron and attract by a magnet. Let's now discuss about the magnetic properties of O2. This molecular orbitals diagram show how atomic orbitals of two oxygen atoms combine to form molecular orbitals. When we fill the electron according to the Aufbau principle, which we fill with 16 electron valence, we notice importance at the highest energy levels. I already been highlight for the 2 pi star 2py and pi star 2pz antibonding orbitals, each contain with one unpaired electron. This unpaired electron make it paramagnetic. Comparison magnetic properties of O2 in molecular orbital theory versus valence bond theory. First, let's take a look at the valence bond theory. It predicts a diamagnetic while the molecular orbital theory predicts a paramagnetic. So, for the valence bond theory, electrons are localized in bonds or lone pair between specific atoms, while molecular orbital theory, electrons are delocalized across molecular orbitals over entire molecules. So, when I do a Lewis structure for O2, for the valence bond theory, I get a 12 valence electron that was paired, which is 2 lone pair on each atom and double bond at the middle of O2. For the double bond, it consists with a sigma bond and pi bond, while the molecular orbital theory we get a 2 electron remain unpaired in degenerate antibonding orbitals. From this video, we can see that liquid oxygen is attracted by a magnetic field. It's proof that O2 is paramagnetism. This occurs because O2 has two unpaired electrons in pi star 2py and pi star 2pz, which align with the molecular orbital theory.
Conclusion. In summary, molecular orbital theory provides a comprehensive explanation of electron distribution within a molecule. Through this theory, the molecular orbital diagram of the O2 molecule can be constructed by illustrating the formation of both bonding and antibonding orbital. The calculation of bond order from the molecular orbital electron configurations allow accurate prediction of molecular stability and bond strength. Furthermore, molecular orbital theory successfully explains the paramagnetic nature of oxygen due to the presence of unpaired electrons, which cannot be adequately explained by valence bond theory. Overall, molecular orbital theory offers a more accurate and detailed understanding of chemical bonding, molecular stability, and magnetic properties. That's all from me. Thank you.
All of these are the references that we use to make the presentation about molecular orbital theory.